Hey you all, this is Dr. Habib Ahmed. I welcome you to my YouTube channel. Today we delve into the fascinating world of solar cell thermal analysis using Silvaco TCAD simulation. We are specifically focusing on germanium solar cells, exploring their behavior across different temperatures. We will look at the performance of germanium solar cells at temperatures of 295 Kelvin, 300 Kelvin, 305 Kelvin, and 310 Kelvin. Through the powerful tools of Silvaco TCAD, we will observe how these variations in temperature impact the performance and efficiency of our germanium solar cells. Whether you are a student, researcher, or solar technology enthusiast, this simulation will provide valuable insights into the thermal management of solar cells. Don't forget to like, subscribe, and hit the notification bell to stay updated on our latest simulations and analysis. Let's harness the power of knowledge together. Before running the simulation, let me tell you about the impact of temperatures on the performance of solar cells. Temperature has a significant impact on the performance of solar cells. Generally, as the temperature increases, as you can see over here, we see lower voltage output for our solar cells. So higher temperature lead to a decrease in the voltage output of solar cells. This is a result of increased intrinsic carrier concentration in the semiconductor material, which reduces the built-in potential. Also, as the output voltage decreases, you also see reduced power output, and I'm going to show that in my simulation as well. I've compiled the result in Origin, and then I plotted them together on the same figure for comparison purpose. The overall power output of solar cell decreases as temperature rises, mainly because the decrease in efficiency and voltage outweighs any increase in current. So if you look over here at this figure, you see a significant decrease in the open circuit voltage of this solar cell. Although there is an increase in the current of the solar cell, but this current increase is minute. It's not significant. So the decrease in efficiency and voltage outweighs any increase in current because the current increase is not significant. So there is a decrease in efficiency. The efficiency of solar cells typically decreases with rising temperatures. This is primarily due to increased electron-hole recombination rates and reduced open circuit voltage. It's really important to perform thermal management of our solar cells. We have to design our solar cells in a way that we take into consideration the temperature variations as well. Effective thermal management becomes crucial to maintain or improve the performance of solar cells. Techniques like cooling systems or designing for better heat dissipation can mitigate some of these losses. Also, temperature variations have impact on longevity of the solar cells as well, especially at high temperatures. High temperatures can accelerate the degradation of materials and reduce the lifespan of solar cells over time. So, in summary, while solar cells generate electricity from sunlight, their efficiency and performance are inversely affected by temperature. Or you can also say the efficiency and performance of solar cells are adversely affected by temperature. Effective management of heat is essential for optimizing their output and longevity in various environmental conditions. These are actually the slides of one of my lectures on solar cells. The other slides are not really relevant to this video tutorial, so I'm gonna skip those. And then, so I worked on the Silvaco TCAD simulation of a germanium solar cell. And here is the structure of the germanium solar cell. I've already studied like a lot of other solar cells based on gallium nitride materials, gallium arsenide materials. I've posted a lot of videos on perovskite solar cells as well. I've posted videos on multi-junction solar cells as well. So you can actually apply today's thermal analysis to any kind of solar cell structure. I'm giving the germanium solar cell just as an example, and also because I have not covered a single junction germanium solar cell so far in my simulations. Germanium solar cell is also crucial, specifically in multi-junction solar cell, because germanium's band gap, which is 0.67 electron volts approximately, bridges different semiconductor materials in multi-junction solar cells, improving photon absorption across sunlight's spectrum. Also, it enables high conversion efficiencies by optimizing light absorption and spectral splitting between different layers. So here is a germanium solar cell structure, and it's running from 0 to 100 micrometers in the y direction, and from 0 to 1 micrometer in the x direction. Let me zoom in over here at the top of the structure. So the germanium solar cell actually has a layered structure where we have indium gallium phosphide top window layer, followed by a germanium emitter layer, and then the germanium base represents a sophisticated design aimed at optimizing solar cell energy conversion efficiency. The indium gallium phosphide layer over here at the top serves as a top window, providing excellent transparency to sunlight while effectively passivating the surface to minimize recombination losses. Below the indium gallium phosphide window layer, we have the germanium emitter layer, facilitating efficient electron hole separation upon photon absorption, and it is crucial for maximizing current generation. Next, we have the germanium base layer, which is really thick as well, and it actually forms the core of the solar cell, where majority carrier are collected. This layer is designed to ensure efficient carrier extraction and transport, contributing significantly to the overall cell performance. Together, this layered structure highlights a strategic balance between transparency, light absorption, and carrier collection efficiency, essential for achieving high solar conversion efficiency in germanium-based solar devices, or you can say photovoltaic devices. Now, let us start working on the code. So I open the direct build window for simulation, and here I already saved codes for the Silvaco TCAD simulation of germanium solar cells, and also to look at their thermal analysis. So let us start with the 295 Kelvin temperature. And before running the simulation, let me give you a description of the structure of the solar cell. So I start with meshing. My structure runs from 0 to 1 micrometers in the x direction. And let me open a figure over here. So my structure runs from 0 to 1 micrometer in the x direction and from 0 to 100.2 micrometers in the y direction. And in this part, I will define the meshing. If you look at the structure, I have actually introduced denser meshing at interfaces and also for the thinner regions. But for the thicker bulk regions, I have introduced sparser meshing. Then we define different regions. For example, my region number 1 is indium gallium phosphide, running from 0 to 1 micrometers in the x direction and from 0 to 1 micrometers in the y direction. And it has a gallium content of 50%, as you can see over here. So as you can see, it's running from 0 to 1 micrometers in the y direction. Then region number 2 is germanium, running from 1 to 1.2 micrometers in the y direction. So region number 2 is germanium emitter, running from 1 to 1.2 micrometers in the y direction. Region number 3 is also germanium, running from 1.2 to 100.2 micrometers in the y direction. So it's actually this thicker germanium base layer. Then I have introduced anode at the bottom and cathode at the top. Over here, I save the structure with this name. Then I start working in another module of Atlas Silvaco TCAD, where I call this already saved structure. I define doping for different regions. For the indium gallium phosphide layer, I have introduced N-type doping of 1 into 10 to the power of 18 per centimeter cube. Then for the germanium emitter layer, I've introduced an N-type doping of 6 into 10 to the power of 18 per centimeter cube. Similarly, for the germanium base layer, I've introduced a P-type doping of 1 into 10 to the power of 18 per centimeter cube. Since this bottom layer is P-type, so that's why I've introduced anode over here at the bottom. And the top layer is N-type, so I've introduced cathode over here at the top. Then I actually introduced the absorption properties for these different materials. For germanium, I just include the command of sopra is equal to germanium.nk. These are the Silvaco TCAD already has absorption properties for a lot of materials, including germanium. So in order to include those absorption properties, we just write sopra is equal to material name. There are like different material files. You can look at this manual if you are working other materials. However, it does not have absorption properties for all materials. For example, it does not have absorption properties for indium gallium phosphide. So for indium gallium phosphide, we manually have to write down the absorption properties of indium gallium phosphide in a .nk file, where n represents the refractive index and k represents the absorption coefficient. So as you can see over here, I have 1000 entries of triplets. So in the first column, I've introduced the wavelength. In the second column, I've introduced the refractive index of indium gallium phosphide. And in the third column, I have introduced the absorption coefficient for indium gallium phosphide. In order to call this file into Silvaco TCAD, we write index.file is equal to indium gallium phosphide.nk. Then we introduce different models for running our simulation, followed by, now this is the crucial section over here. So in order to include the thermal analysis of these germanium-based solar cells at different temperatures, we include this model, lat.temp, which actually enables heat flow simulation for this germanium solar cell, followed by making a thermal contact to the structure at the bottom of the structure. Now, as I already told you that my structure is running from 0 to 100.2 micrometers, so I actually make a thermal contact at 100.2 along the y direction, or you can say at the bottom of the structure. And I've set the temperature of this structure to 295 Kelvin. Here I want to look at different output parameters like the energy band diagrams and some other parameters. Here I've included the Newton method for the simulation for the solution, or you can say for calculating the solution of these semiconductor devices. And here MaxTrap actually introduces a procedure so that our simulations can be repeated up to a maximum of 20 number of tries set by the method using the MaxTrap parameter. And we do this because sometimes we might face convergence problems with our solar cells, and once the convergence is obtained, the bias steps are increased once again. So for convergence, it's going to reduce the step size with every new iteration, and once we achieve the convergence, the bias steps are increased once again. Over here we save and plot the structure. Then I want to look at the IV characteristics of the solar cell under dark conditions, and then I want to look at the IV characteristics of the solar cell under light conditions. I've conducted the device simulation at AM 1.5 G, as you can see over here, or we can include G. A diffused spectrum represents a diffused spectrum, which is 1000 watt per meter square, or you can say 100 milliwatt per centimeter square. So actually the solar spectrum typically extends from the infrared to the ultraviolet region, where the wavelength ranges from 0.2 micrometers to 3 micrometers. But the intensity is not uniform. There is a difference in spectra measured at the top of the atmosphere and at the surface due to atmospheric scattering and absorption. The path length of light in the atmosphere depends on the angle, which will vary with the time of the day. And this is given by the year mass number, which is the secant of the angle between the sun and the zenith, or we can say the vertical axis. So AM1 represents when the angle is of the sunlight to the vertical axis is 0. Similarly, AM2 is when the sun is at an angle of 60 degrees to the vertical axis. And AM 1.5 is when the sun is at an angle of 48.2 degrees. So there are certain standard test conditions for measuring the performance of solar cells, and these standard test conditions are room temperature, AM 1.5, or the sunlight should be at an angle of 48.2 degrees to the vertical axis, and the power should be 1000 watts per meter square, or in other words you can say 100 milliwatts per centimeter square. So over here in this step we actually introduce AM 1.5 spectrum at these coordinates for our solar cell, and then the next step in solar analysis is to illuminate the device. So we can turn on the incident light by assigning the beam intensity on a solve statement, and we had assigned AM 1.5 on the beam statement. This corresponds to standard test conditions, or you can say 1000 watt per meter square. This actually represents one sun, a beam of one sun. But sometimes, in some cases, we may encounter convergence difficulties, and we may need to ramp the sunlight intensity from 1 milliwatt per meter square to 1 watt per meter square. And that is what we did. In different steps. So in this step, we actually illuminate the device, and next we extract the illuminated forward biased current voltage characteristics. So first we define an output log file for capturing the data, and then we run a sweep from 0 to 0.35 volts for the germanium based solar cell, and then we use the overlay command in order to plot the dark and light IV characteristics in the same figure. And then we plot the structure under light conditions as well using these commands. Here we call this file, which has the light IV characteristics of the germanium based solar cell, and from this we extract the short circuit current density, and the short circuit current density in milliamps per centimeter square can be calculated using this formula, where this actually represents the area of the device, which is 1 micrometer by 1 micrometer, and we convert it into centimeters, centimeter square, and this actually we include 1000 in over here as a multiplication factor, because we actually want to look at the current density in milliamps per centimeter square. Similarly, we can extract the open circuit voltage, the maximum power, maximum voltage, maximum current, the fill factor, and the efficiency of the solar cell. Next, we start working in another module of Atlas, Silvaco TCAD, where just like the previous section, we introduce different material properties, and then using this section, we actually look at the internal and external quantum efficiency of the solar cell, and then we plot them onto the same figure using this overlay command. So this is a short description of the code, but we are mainly interested in this section. So we want to look at the performance of the solar cell at 4 different temperatures: temperature of 295, 300, 305, and 310 Kelvin. And then we want to compare the performance of these of the germanium solar cell at these 4 different temperatures. So what I'm going to do is I'm going to run 4 different simulation windows. So here is the first one, and then I'm going to open 3 more windows. So if you did not know, I got a good news for you. You can actually perform multiple simulations simultaneously for Silvaco TCAD simulation. I was actually working on a multi-junction solar cell project, and working on multi-junction solar cell, especially if you're working on triple junction and quadruple junction solar cells, it's really complicated. It's really time intensive. So like initially I was performing simulation one by one, varying certain parameters, the doping concentrations, the layer thicknesses, the content in of a particular material internally, alloys and that kind of stuff, looking at the tunnel junctions, including and excluding some layers, and it was taking me a long time. I spent a month on this, and then I thought about, can we like run multiple windows simultaneously? And it was a pleasant surprise for me when I came to know that we actually can. And after that, I can really optimize my simulation and save a lot of time for me. For nanotechnologists, time is money. So if you can find efficient ways of saving time, you can actually make a lot of money. So so I already have the code for the germanium solar cell at a temperature of 295 Kelvin. I'm going to include three more temperatures. I will already define the codes for this. So I open this file at 300 Kelvin. And then I open this file. So let me do it again. Like, I want to do it in sequence. So in the first window, I opened the code for 295 Kelvin temperature. In the second window, I want to open the code for 300 Kelvin temperature. In the third window, I want to open the code for 305 Kelvin temperature. I want to be more organized, that's why I had to reopen it. And in the fourth window, I want to open the code for a temperature of 310 Kelvin. Okay, and then I start running the simulation one by one. This for the first window, second one, third one, and the fourth one. Cool, we already got the figure for the first one. And here is the structure under thermal equilibrium. The first figure is open, and under thermal equilibrium the rest of the structure is also going to be the same. So I'm going to close the rest of the structure. I just want to work on one structure under thermal equilibrium, and then the code is running for the remaining part. So here is the structure. You can actually right click on the structure to display meshing. Click on it once again, hit apply to enable it. You can zoom in on the structure to see different parts. For example, indium gallium phosphide. You can also see this thin layer of germanium emitter now. Also, we can right click on the structure, go to display, click on contours, go to define contours, and I'm actually looking for net doping. Here it is. So you can click on net doping to see the doping levels and type of doping for different layers over here in this structure. So this one is like you can see from this color chart. This one is p-type, and its doping is approximately 10 to the power of 18. Similarly, this one is n-type with a doping level of 10 to the power of 18. This one is p-type once again. Or if you want to specifically look at the numbers, you can always click on tools, go to cut line, draw a vertical cut line across the structure, and now these are your exact doping levels. 1 10 to the power of 18 per centimeter cube over here at the top, and this is n-type doping. Then this is 6 into 10 to the power of 18 per centimeter cube, and from this doping profile you can see that this is p-type. Is it? No, this is n-type. Yeah, so the top one is also n-type, and this is also n-type. And then the doping level of the germanium base is 1 into 10 to the power of 18 per centimeter cube, and once again this is p-type. Or let me do one thing, go to display, go to define contours, click on linear, if that gives me a better picture. Yeah, this gives me a better picture. Okay. So now you can see that the top layer has a doping of 110 to the power of 18. Similarly, this layer also has a doping of 110 to the power of 18, and this layer has a doping of 610 to the power of 18 per centimeter cube. You can disable this part, and we can look at some other parameters. For example, we go to tools, cut line, draw a vertical cut line across the structure. Here we can go to display, and we can look at the energy band diagram, AC of T, EV of T, electron QFL, and hole QFL. Hit on apply, and we got to disable the net doping. Hit apply, click OK. So here is the energy band diagram of the structure. Click on delete. We can disable these stars and hit apply once again. Similarly, you can disable these interface lines. Click on apply. So you see, like over here we have the indium gallium phosphide layer, and it has a wider band gap. Then we have the germanium N-type layer, and then we have the germanium P-type layer over here on the right. How do we know that this is P-type? How do you know that this indium gallium phosphide layer is P-type? Similarly, now the code is running, giving us different structures. How do we know that this indium gallium phosphide layer is N-type? Similarly, this germanium emitter layer is also N-type, and this germanium base layer is P-type, because we can figure it out from the Fermi level. The Fermi level is close to the conduction band in case of this layer, and also this germanium emitter layer. However, it's close to the valence band for this germanium base layer. So that's how we know that this layer is N-type, this layer is N-type, and this layer over here is P-type. We can also figure out for sure the band gaps of these different layers. By clicking on EG and hit apply. So the band gap of this indium gallium phosphide layer is 1.9 electron volts, and it is approximately 0.67 electron volts for germanium. Now we got different figures. So first we look at this figure, and I want to look at the IV characteristics of this solar cell at 295 Kelvin. So instead of the global device temperature, I click on cathode current and then hit apply. And here is the IV characteristic of the solar cell at 295 Kelvin. Then we have the power curve for the germanium solar cell at 295 Kelvin. Then we have the structure under light conditions for germanium at 295 Kelvin. So I right click on the structure and click on contours, go to define, and then contours once again. And I'm actually looking for photo generation rate. So here is the photo generation rate. Hit apply. This way you can see the photo generation rate in different layers. And if you want to look at the numbers, go to tools, cut lines, draw a vertical cut line across the structure. Now we can delete this part. And you can see that the photo generation is exponentially decreasing. If you also want to look at the photo generation inside the indium gallium phosphide layer, we can zoom in on this curve, and we can see that here is the photo generation rate level for the indium gallium phosphide layer, and it's exponentially decreasing. And then here it is for the germanium cell, exponentially decreasing with depth. We can also look at the internal and external quantum efficiency of the solar cell. And then hit apply. So the red curve represents the internal quantum efficiency. The blue curve represents the external, the green curve represents the external quantum efficiency. And the blue curve actually represents the external quantum efficiency of the germanium solar cell while taking into account the absorption of the germanium material as well. This figure shows us the spectral response range of the solar cell. Click apply. So here you can see here is the spectral response range of the germanium solar cell. On the y-axis we have current. However, you can also look at the responsivity of this germanium solar cell by dividing this current on the y-axis over the power, input optical power. You don't need the spectral properties of the solar cell anymore, so I'm gonna close these curves. Again, also I don't want to look at the photo generation rates anymore, so I'm gonna close these curves as well. Here we can go to display, and we can look at the IV characteristics of these at different temperatures. This curve is at a temperature of 300 Kelvin. Then this one is, if we set it up, is at a temperature of 305, and this one is at a temperature of 310. Similarly, we have the power curves at different temperatures, but it's going to be difficult to look at these individual figures and to make a comparison out of it. So for comparison purpose, I've actually plotted them into origin. So I exported these into Excel files. As you can see over here, I exported the dark and light IV characteristics into Excel files. Similarly, I exported the power curves into Excel files. Here are the PV characteristics of the solar cell. Similarly, I have exported the spectral response range of the solar cell into Excel file. But I'm mainly interested in looking at the IV and PV characteristics of the solar cells. So for all the 4 temperatures, I plotted them together. I worked on 2 origin programs, one for a comparison of the IV characteristics of the germanium solar cells under light conditions, and the second one for looking at the PV characteristics of the germanium solar cells. So let's open the first one. So from all the Excel files, I entered the results over here, and then I plotted this figure. Let me full screen it. So here you see a comparison of the IV characteristics of the germanium solar cell at temperatures of 295, 300, 305, and 310 Kelvin. As you can see that with the increase in temperature, the short circuit current density slightly increases. There is a really slight increase, like minute, insignificant increase in the short circuit current. However, there is a significant decrease in the open circuit voltage of the germanium solar cells with increase in temperature. If you want to look at the values, so we can click on this icon to look at variables. For at 295 Kelvin, look at the numbers. Here is the short circuit current density, 42.918, and then perform a comparison of this for the remaining as well, 42.959 at 300 Kelvin. Similarly, 42.9961 at 305 Kelvin. Similarly, 43.0296 at 310 Kelvin. So there is an increase in the short circuit current density, but this increase is minute. However, now look at the open circuit voltages of these of the germanium solar cell at different temperatures. It's 0.307 at 295 Kelvin, 0.296 volts at 300 Kelvin, 0.286 volts at 305 Kelvin, and 0.276 I would say at 310 Kelvin. So there is a significant decrease in the open circuit voltage. Also, you might see, let's perform a comparison of the efficiency of the germanium solar cell at different temperatures. So the efficiency is 9.62 at 295 Kelvin, and ignore this negative sign. It's just about the formula. I can always put a negative sign in front of this formula and make it positive. So don't get confused about the negative sign. It's all about using the numbers, using signs in the formula. For convenience, I did it this way, but we can make it positive. So the efficiency is not 9.62 at 295 Kelvin, 9.19 at 300 Kelvin, 8.74 at 305 Kelvin, and 8.31 at a temperature of 310 Kelvin. So there is a significant decrease in the efficiency of the solar cell with increase in the temperature as well. Now look at the fill factor, 73 at 295 Kelvin, 72 at 300 Kelvin, 71 at 305 Kelvin, and 70 at 310 Kelvin. Why is that so? In order to understand that, let's look at the power voltage characteristic curve. So I'm going to open this origin file as well. Now here you can see that there is, with increase in temperature from 295 to 310 Kelvin, there is a significant decrease in the maximum power of the solar cell. Like the maximum power is decreasing, and also as the maximum power is decreasing, the maximum current IM and the maximum voltage is also decreasing with increase in temperature. And as you know, that fill factor is the ratio of maximum voltage times maximum current divided by open circuit voltage times short circuit current. So if the maximum current and the maximum voltage is decreasing, the fill factor would also decrease. And if these numbers are decreasing, the efficiency is also going to decrease. So there is a significant impact of temperature on the performance of solar cell. And that concludes the simulations part. Thank you for joining us on this journey through thermal analysis of germanium solar cells using Silvaco TCAD simulation. If you enjoyed this video, be sure to give it a thumbs up and subscribe to our channel for more insightful simulations and analysis. Feel free to leave your comments and questions below. We love hearing from you. Until next time, keep exploring, keep learning, and keep innovating. See you in the next video. Take care. Adios.